Okay. Unit 4. There's a number of components to Unit 4. It's 9 lessons long. It's going to take a while to get through. Our goal is to get through, for sure, 4.1 through 4.3 and have a test on that before you're done. Okay, so before you're done with a semester. Okay, so until June, yeah. So just before semesters end, we need to get through 4.1 through 4.3. Now, what are we going to be doing? This will really summarize it for you. This is, there's certain parts that your professors next year are going to want to make sure that you know and understand. And there's certain things as you leave calculus, people are going to say, well, you learned that, didn't you? And one is that you would use the formal definition of the derivative, f of x plus h minus f of x all over h. You guys know how to do that. Another thing is that you guys know how to use the chain rule, the product rule, and quotient rule. You know how to do that, right? Okay. Is related rates a big component? It's becoming much more popular and significant to do. It didn't used to be part of the AP standards, but it currently is. So that's why we cover it. It is good stuff. But what we do here, I would say, really encompasses all of what we would refer to as differential calculus. So you guys are currently in Calc 1 doing differential calculus. Calculus 2 is sometimes referred to as integral calculus. And that's a little bit different. And it's exciting. We're going to do a lot of it, as we should. But here's really the deal. You guys graphed these type of shapes last year. In fact, I just gave a test in pre-calculus on how to graph quartic polynomials. But you always had this question. You said, Mr. Gens, I know where it crosses through the x-axis. But I don't know necessarily how high it goes in between or how low it goes. After this unit, you guys will be able to graph anything and every single aspect of the graph without the use of any calculator. So that's where we want to get to. It's very cool. We start out with this. Absolute maximum is sometimes referred to as a global maximum. Largest value of the function over its domain. So if you look at this graph to the right, let's suppose that this was the entire graph that didn't continue on to infinity on either the left side or the right side. It stops from -3 to +4. So this is the given domain. So we're -3 to +4. What would be the absolute maximum? 64. That's an absolute max. You would have an absolute value, absolute maximum value of 64. Exactly. Absolute minimum. Smallest value of the function over its given domain. So do you see the absolute minimum? -152. Those aren't so interesting. What are more interesting are local or relative. They go by both names, so be familiar with them. I call them local. Okay? The local maximum is going to be f of x greater than, to attach an equal sign. Actually, let's rewrite that. Your book writes it the other way. Let's go f of c greater than or equal to f of x, or x near c. So let's suppose for a second, let's look at 1. Let's say 1 is that c value. If I plug in 1 to the function, my output is 37. Would you agree that for the immediate region surrounding 1, that 37 is the largest value? Now, the question is, what is that immediate region? Well, you could define it, really infinitely small if you wanted to. It doesn't have to be, within 1 unit or 2 units. Really, the idea is you can look at the graph and identify that's going to be a local max. Do you see a local min? That's going to be a local min. Right here at negative 27. Negative 27 is the local min. Is negative 27 the absolute minimum? No. Is 37 the absolute maximum? No, it's just locally it's the largest or smallest value. Here's another one. This is also a local. It just also happens to be the global one. So, yes. What's that? Nope. Right. That's how we will define it, yes. So, Fermat's theorem, which relates to exactly what you guys are talking about because you're asking that question. If f has a local maximum or minimum at C, and if, let's see if we can just identify it first. As you guys look at these spots where you have local max or local mins, you notice anything interesting? Think calculus. Think derivative. Yeah. See, if you were to draw a tangent line, what is the slope of that tangent line? 0. So you can see that if there's a local maximum or minimum at C, and if f prime of x exists, then f prime of x, or I'm sorry, f prime of C should be equal to 0. The derivative of that spot should be equal to 0. So when we talk about local maxes or local mins, the derivative should be equal to 0 at that spot. Now, as we're sketching graphs, we like to identify critical numbers. A critical number is a function f is a number C in the domain of f such that either f prime of C is equal to 0. That'll be one situation where you have a critical number. The other possibility is that f prime of C does not exist. Any situations where those occur, we have to find them because something interesting happens with the graph. Now, let's really press your minds here. If f prime of C does not exist, true or false, I have to have an asymptote there. False. Why? You could have what we call a vertical tangent. So here are the examples, classic examples of critical points. Let's suppose that you have a graph that looks like that. You can see that you have a critical point right here. That is a critical point because you have a vertical tangent. If you have a vertical tangent, f prime of C does not exist. The slope would be undefined. Because the slope is undefined, the derivative does not exist. That's an example of a critical point. So you can have a smooth curve. It can be defined on every value of the domain. Here's another example where you would have a critical point. if you remember from our great examples up here, some people drew examples where the functions are not differentiable, and one would be at a corner. So suppose you had the absolute value of x. That would be an example where you, again, have a critical point that exists right here. You have to find that. Something interesting happens at that spot. You could have a situation where the function is undefined. That looks like this. So we have a critical point at 0. Because the function is undefined, it has vertical asymptotes. And the last one is the one we just talked about. You could also have graphs that look like this. Anywhere where the derivative is equal to 0, so we could say, right there, I tried to draw it the best I could. Suppose you had a triple root. That would be an example of a critical point. Here's a critical point where you have, again, the derivative equal to 0. So those are all points. So if this is a critical point, does it have to be a local max or min? No. If the derivative is equal to 0, it doesn't mean that it's for sure a local max or min. However, if it is a local max or min, then we'll find out that the derivative is equal to 0. Let's flip it over and see if we can do a couple examples real quick. Find the critical numbers of the function. Is there anywhere where that function is undefined? Nope, it's a nice polynomial. Polynomials are generally defined over entire domains from negative infinity to positive infinity. So what I need to do now in order to find the critical points is I need to find where f prime of x is equal to 0. What is f prime of x? Yeah. Does that factor? If it didn't factor, we would use the quadratic formula. This does factor. I have 0 equals 3x minus 1. I'm sorry, times x minus 1. What are your solutions? So I have critical points at x equals 1/3 and 1. That is the answer. Not too bad, huh? Let's look at B. Is there any point where B is undefined? 0. So undefined at x equals 0. So therefore, we know we have a critical point there. We must also take into consideration the derivative, where the derivative is equal to 0. In order to find this derivative, I need to use the quotient rule. What is the derivative of the top? 2x times the bottom, 2x squared. Minus, what's the derivative of the bottom? 1 times the top, x squared, plus 1 because I have to distribute my negative through. Thank you. Practice. Divided by, what's in the denominator? X squared. So f prime of x would then be equal to x squared plus 1 over x squared, right? Now, let's think about this, people. This is where your analysis minds need to come into play. Where is the derivative undefined? Have we already accounted for that spot? Yes, we did. Second of all, we need to consider where the derivative is equal to 0. The derivative is equal to 0 when the top is equal to 0. So I don't have to worry about the bottom when I'm finding where it's equal to 0. I just focus on the top, because if the top is 0, the whole thing will be 0. So if you say x squared plus 1 equals 0, when you solve that, what do you get? X squared equals negative 1, so x is equal to plus or minus I. So is there anywhere in the real set of numbers where the derivative is equal to 0? No. If there was, I would include those. But I don't have that. So all I have in this situation is that I have critical points at x equals 0. That's it. So if the function is undefined there, is that going to have any local mins or maxes? No, it doesn't. And that helps me as I obtain knowledge about it, about how to sketch it. We're doing just one example, critical points. You guys will have about 8 of these by the time we're done that you will lay out. And you'll be very good at it. You'll be very efficient with it. Trust me. What does this look like? Absolute value. What part of it do we need to find where it's undefined? Yeah, where it switches to positive and negative. So we need to find that spot, right? We need to find this spot right here. I need to find where it switches. Okay? I can set this one equal to 0. I can. Does this ever have a local max or local min? If we were to take the derivative of the left and the derivative of the right, we would just get negative 3 and positive 3. You're never going to have a local max or min. But this point is critical. If you notice, this graph is just shifted over 2 units. I take 3x minus 6, and I set it equal to 0. I get 3x is equal to 6. Divide by 3. And we get x is equal to 2. So you have a critical point at x equals 2. That's it. Okay. Now, yes, you said this is like Algebra 2. We're going to start with doing some of these basic things, but you guys, you can see in Algebra 2, we spent a lot of time on polynomials, a lot of time on rational expressions, a lot of time in absolute values, and a lot of time on radicals. Now, it's all in one example. So we got to be good with our algebra. We don't have time for that. That takes a while. I'm going to put your assignment. I'm putting your assignment on the board to get started on, you guys. My uncle passed away yesterday morning, so I got to go to a funeral tomorrow. I don't know if it's in the afternoon or morning, so I might be or I might not. I have 3 kids at home and a wife who are puking right now. So I shouldn't have this on, should I? Okay. Okay, there's a good place to start. I'll probably give you more tomorrow.